In this topic, we're going to look at how to take real-world optimization problems and formulate them as a linear programming problem. If a problem involves several variables, sometimes it can be helpful to formulate it as a linear programming problem. An example of a type of problem that might be used could be a farmer wishing to decide how many of each type of crop to grow in order to maximize their profits, or a person who's trying to organize transport and deciding how many buses and minibuses to book in order to minimize the total cost of a trip. Linear programming reduces a problem to a series of inequalities. We call these inequalities constraints, which we then plot onto a grid and solve. For each of the following constraints, pause the slide and write down an inequality that satisfies the situation given. So the first one, if a company needs to build at least 300 computers a week and the number of computers that the company makes per week is X, write this as an inequality or a constraint. So the answer to that is X is greater than or equal to 300. Next, write as a constraint this problem. The company needs to make at least 300 computers per week, but they only have space to store 500 per week, and the number of computers made per week is X. So as an inequality, X would need to be greater than or equal to 300 and less than or equal to 500. Next, a factory makes X doors per day. So this one maybe isn't obvious, but this is more of a trivial constraint. X needs to be greater than or equal to 0. Next, a factory makes two types of sofas, standard and luxury, and the factory needs to make at least 20 of each type of sofa. If the factory makes X standard sofas and Y luxury sofas, can we write this as a constraint? So the answer for this is that X has to be greater than or equal to 20 and Y also has to be greater than or equal to 20. This time the factory makes standard and luxury sofas and they can only make 100 sofas altogether. So this time the constraint becomes X plus Y is less than or equal to 100. So now the factory makes standard sofas and luxury sofas, and the number of people required to make each sofa is 3 people to make a standard sofa and 5 people to make a luxury sofa. The workforce has 90 people altogether. Can we make a constraint involving this? So this time we need to take 3 times the number of standard sofas, which is 3x, and 5 times the number of luxury sofas, 5y. That will give us a total number of people required in the workforce. And because 90 is the maximum number of people that can be used, the inequality is 3x plus 5y is less than or equal to 90. So we're now going to look at a constraint involving the amount of cloth available at the factory. So the factory is making X standard sofas and Y luxury sofas, and each sofa uses 2 types of fabric, cloth A and cloth B. Standard sofas need 3 meters of cloth A and 5 meters of cloth B, while luxury sofas need 6 meters of cloth A and 2 meters of cloth B. The factory has 120 meters of cloth A and 100 meters of cloth B available. So in order to write a constraint here, it's often easier to first of all put the information into a table. So put the types of cloth down the side. We'll put the types of sofa, so standard, and there are X of those, and luxury, there are Y of those. So if we put the information into the table, we know that a standard sofa needs 3 meters of cloth A and 5 meters of cloth B. A luxury sofa needs 6 meters of cloth A and 2 meters of cloth B. So the amount of cloth A available is 120 meters. So this tells us that cloth A, the value needs to be less than or equal to 120. And for cloth B, we have 100 meters. So this is less than or equal to 100. We can now read along the row and write down the two inequalities. So the top row gives us 3x plus 6y is less than or equal to 120, and the bottom row gives us 5x plus 2y is less than or equal to 100. We now have a similar problem involving a travel agent offering two types of tours, amaze and stunning, and the two tours visit two different locations, Site A and Site B. The amount of time taken at each site is given below, so the amaze tours need 90 minutes at Site A and 30 minutes at Site B, while the stunning tours need 50 minutes at Site A and 25 minutes at Site B. Site A is open for 6 hours a day and Site B is open for 5 hours. So in order to write this as a constraint again, we're going to put the information into a table. Going to put the sites along the side, A and B, and then put the types of tours across the top. So, amaze tours, there are X of those, and stunning tours, there are Y of those. So we're going to put the information into the table. So we're going to do it all into minutes, so that means that the times in hours are going to need converting. So amaze tours need 90 minutes at Site A and 30 minutes at Site B. Stunning tours need 50 minutes at Site A, 25 minutes at Site B. The Site A is open for 6 hours, so 6 times 60 is 360. This means that the amount of time taken at Site A needs to be less than or equal to 360. Site B is open for 5 hours, 5 times 60 is 300 minutes. So the amount of time used at Site B needs to be less than or equal to 300. So that leaves us the two inequalities. 90x plus 50y is less than or equal to 360, and 50x plus 25y is less than or equal to 300. Sometimes you'll be given a problem and asked to formulate it as an optimization problem. This means that you will first need to define the variables if they haven't already been defined in the question, then list the constraints in terms of the variables, and then write down the objective line, which is the thing that we're either trying to maximise or minimise. So we're going to look at this problem here. This is the travel agent offering amaze tours and stunning tours. We can see in the second from last line that X and Y have already been defined. X is the number of amaze tours, Y is the number of stunning tours. So we don't need to define that again. However, if that line wasn't given, you would need to define X and Y yourself. Pause the slide now and write down the constraints. Also write down the objective line, which is the thing that we are trying to maximise. So the first constraints are that the travel agent must offer at least 3 of each tour. So X needs to be greater than or equal to 3, and Y needs to be greater than or equal to 3. The number of tours in total needs to be at least 8. This means that X plus Y needs to be greater than or equal to 8. We would then put the information into a table to make it easier. We would end up with 30x plus 40y is less than or equal to 450. That is coming from the amount of time spent at Site A. We would also get 20x plus 45y is less than or equal to 420. That is coming from the amount of time at Site B. Both of these can be simplified. We are trying to maximise the profit. So the profit is coming from the commission, £40 from the amaze tours and £70 from the stunning tours. This means that the total commission will be 40x plus 70y. We need to use the word maximise to show that we are trying to make this as large as possible. So these inequalities are the constraints, and this line is called the objective function. Pause the slide now and formulate this problem as a linear programming problem. Don't forget to define what the variables are in the first line. So because the farmer is wishing to decide how much of each crop to maximise, the two variables we're going to use are that X is the number of hectares of wheat and Y is the number of hectares of potatoes being grown. The objective function is P equals 80x plus 100y, and we want to maximise this. This comes from the fact that the profit for a hectare of wheat is £80 and the profit from a hectare of potatoes is £100. The constraints we should have got. Considering the time constraints, we arrive at 30x plus 50y is less than or equal to 2,800. Considering the amount of fertiliser available, we find that 700x plus 400y is less than or equal to 40,000. Note here that we've had to convert the number of tonnes of fertiliser into kilograms because the amount of fertiliser given earlier in the question is in kilograms, so the units do need to match. We also have the trivial constraints that x and y both need to be greater than or equal to 0. Next, pause the slide and formulate this as a linear programming problem. You may find it easier to put the information into a table before you write down the constraints. Don't forget to define the variables first. So we're going to define the variables. The company is going to build X economy, Y standard and Z luxury chairs each week. The objective function is again to maximise the profit, and the profit is given as P equals 50x plus 60y plus 80z. That comes from the profit on each of the three types of chair. We're now going to put the information into the table. So here we're going to put the types of chairs along the bottom on the side and the types of workshop along the top. We're going to fill in the amount of time in hours required for each of the workshops. We've also put the maximum number of hours for each workshop at the bottom. We can now read down the table to write down the constraints. So the first constraint comes from the column of the cutting workshop, which is 0.5x plus 0.5y plus 0.75z has to be less than or equal to 40. Similarly, for the assembly workshop, we get 0.75x plus y plus 1.25z is less than or equal to 50. And for the finishing workshop, we get 0.5x plus 0.75y plus 0.75z is less than or equal to 40. You may choose to multiply each of these constraints by a number, for example 5, in order to make the coefficients integers. This may make it easier to plot the constraints when we come to plot them on a grid. Now please complete this table, formulating each of the three problems as a linear programming problem. The answers are on the next slide.